Hi everyone. Okay, so in this video, and in the next video, which I think will be the last video, I want to talk a little bit about black holes. Okay, so the black hole is one of the crowning jewels of the theory of general relativity. So they're a kind of object that was proposed to exist in the theory, but at the time nobody really believed it, and it wasn't until sort of a few decades later, mid 20th century, that they were actually observed out there in the universe. So just in this first video here, I just want to think about what a black hole actually is. Okay, so if I were to ask you, what is a black hole, can you tell me? Probably what you think of is it's like a kind of cosmic vacuum cleaner. So it's like a big black ball, and just stuff gets sucked into it by gravity. Okay, because it's just a really strong gravitational pull. That is kind of true, although they do get a bit of an unfair reputation. They're not really like giant vacuum cleaners. So a black hole with a certain mass inside it, it behaves really no differently than just an ordinary star or something with the same mass. So particles orbit it in just the same way, really. But we'll think a little bit more about that in the next video. Okay, so about how matter moves around black holes. But in this first video here, we'll just have an introduction to the idea. And so let's go back to the Schwarzschild metric. Okay, and I have rewritten it slightly. Okay, so normally I just write it as ds squared equals, but here I have just written it in terms of c squared d tau squared. Okay, so this is actually just the same as minus ds squared. So I've just multiplied ds squared through by -1, and I've related it to the proper time. Okay, so d tau squared is just -1 over c squared, ds squared. But at any rate, here's the Schwarzschild metric written in this way. And what I want you to notice is something that we haven't mentioned yet, which is that there can be a problem with this metric at a couple of values of r. Okay, so this metric has problems at 2 values of r. Okay, in fact, they're called singularities. Okay, and the first one happens at r equals 0. Okay, if you plug r equals 0 in there, you're going to be dividing by 0. Okay, you'll have 2gm over c squared times 0, and that's a big no-no. Okay, you're not allowed to do that. So that's a singularity, and then there's another singularity that comes from here. Okay, so here you've got a superscript -1, so there is division here. So you get another singularity if what's inside this bracket is equal to 0. So you get another singularity at 1 minus 2gm over c squared r equals 0. In other words, if you rearrange, r equals 2gm over c squared. And this singularity is called the Schwarzschild radius. Okay, it has a special name. Now it's worth mentioning that there are 2 types of singularity in any metric in general relativity. So the first type is a physical singularity, which is what the r equals 0 singularity is. So I'll bullet point these. The r equals 0 singularity is physical. Okay, so there we do have a physical, the curvature of the space-time becomes discontinuous, really, becomes infinite there. But this other singularity at the Schwarzschild radius, that one isn't physical. Okay, it's just an artifact of the coordinate system. And it can be made to actually disappear. If you change and use a different set of coordinates, it will disappear. Okay, so it's just an artifact of the coordinates, nothing physical. But even so, there is something interesting about this Schwarzschild radius. Okay, so that leads us on to the black hole thing. Okay, so talking about Schwarzschild radius. So for most objects, so most stars or planets that are generating their own gravitational fields, this Schwarzschild radius is really small. Okay, really, really small. Look, you've got a c squared in the denominator. So, for example, for the Earth, I actually can't remember the number now. I think I wrote it in the notes. It's like a centimetre or two or something like that. That's the Schwarzschild radius. So it's way, way inside the mass distribution, okay? It's really, really small. But there are some objects where the Schwarzschild radius is actually outside the mass distribution, okay? And that's a black hole. So the entire mass content is actually inside the Schwarzschild radius. And so in that case, you can potentially have other matter outside, like other planets or other things orbiting the mass distribution and getting close to radiuses, getting close to the Schwarzschild radius, and that's where interesting things start to happen. So let's just imagine, let's draw a picture. So let's put down here our gravitating mass. Okay, so this is our mass, capital M. And let's suppose that the Schwarzschild radius is outside. Okay, so let's put it just at this point here. Okay, so this is RS. So this is a black hole in this case, and we'll see why it's called that and what's special about it in a moment. But now let's pick two other points. Okay, so let's pick a point here and call its radius RA, and then pick another one further out and call its radius RB. Okay, so RA is less than RB. And let's imagine that we have a clock at this point, okay, RA, and at this point. Okay, so put a clock here, okay, and another clock out here. And what we want to think about is how these clocks tick relative to each other. Okay, does one go faster or slower than the other? We want to think about time dilation, essentially. Okay, so you've already seen in special relativity that when things move, then you get time dilation. Okay, so a moving clock appears to run slower than a stationary clock. And in fact, a similar thing happens with gravitational fields. So when you have a strong gravitational field, it actually slows time down. Okay, so we're going to see the maths in just a second, but time actually runs slower on this clock than it does on this clock that's further out, okay, in a weaker gravitational field, further away from the gravitating mass. So let's see why that's the case. So let's go over here. So I want you to imagine that these two clocks, now in reality they would want to fall, okay, in towards the mass. But let's suppose that doesn't happen. Okay, so let's just suppose that we hold them here with some external force. Okay, that we just keep them suspended at these positions. So in that case, their space coordinates don't change. Okay, so r, theta, and phi don't change for either of these two clocks. So in both cases, the Schwarzschild metric actually just becomes like this: c squared d tau squared is equal to 1 minus, and you see this 2gm over c squared. I'll just replace that now with I'll just call that the Schwarzschild radius. So let me just call it r subscript s. So we have 1 minus rs over r c squared dt squared. Okay, and then dr squared, d theta squared, d phi squared, they're all 0. And I can cancel the c squared there and there, I suppose. So for clock A and clock B, let's suppose that each of them records some time. Okay, so let's just let some time elapse and allow each clock to record the elapsed time. Okay, so let's imagine a fixed amount of coordinate time dt passes. Okay, so we allow a fixed amount of coordinate time dt, which is like external to both clocks. Okay, it's a property of the whole coordinate system. So we allow a fixed amount of dt to pass, and then the question is, how much time does clock A record? Okay, that'll be d tau A. And how much time does clock B record? That'll be d tau B. So in a fixed coordinate time interval dt, we get that d tau A will be, let's just take square root across, so 1 minus rs over ra dt, which is fixed, and then d tau B, same thing, so square root 1 minus rs over RB dt. And now let's take the ratio of those two to see if one's bigger than the other. Okay, well obviously they're not going to be the same because RA and RB aren't the same. So let's take the ratio, d tau A over d tau B. And so it's this divided by this. dt will cancel dt, and you'll just have the square root of 1 minus rs over RA divided by 1 minus rs over RB. And this, in fact, is less than 1. Okay, how do I know that? Because I know that RA is less than RB. So just as an aside here, we have RA less than RB. So take 1 over both sides and multiply by RS. RS over RA will be greater than RS over RB. And then do 1 minus both sides. 1 minus RS over RA less than 1 minus RS over RB. So you see here, the top line is smaller than the bottom line. Okay, this is smaller than this. So that's why it's less than 1. So that's saying that this ratio is less than 1. So d tau A is less than d tau B. Okay, so clock A in the stronger gravitational field runs slower. It records less time than clock B that's further out. Okay, but that's true. Okay, so far we haven't really used the fact that the mass distribution is wholly contained inside the Schwarzschild radius. Okay, so this will be true for any two clocks in any gravitational field so far. Okay, so for example, if you have a clock just on the surface of the Earth, okay, and you have some other clock up on the space shuttle, the one on the Earth runs slower. In fact, and you might think this is going to be bound to be such a small effect, but it's actually important in sat-nav. Okay, so your satellite navigation system has to have this effect programmed into it to stop the time going out of sync with the satellite. And in fact, I believe they have even measured it, like for distances of 1 meter above the surface of the Earth. So they have even measured in the lab 2 clocks, one on the ground and one a meter higher, and they can see the one on the ground running slower. Okay, so it really is an important effect. But now we're going to take the sort of extreme case, and this is where we get into the idea of black holes. So let's suppose that the clock A, that we bring it in really close to the mass, okay? Bring it into really, really strong gravitational field. Let's let it approach the Schwarzschild radius. Okay, so now we're going to assume that the mass distribution that generates the gravitational field is all inside the Schwarzschild radius, packed in there. And so then we have empty space outside, and we are able to bring this clock in. So we will I'll do it over here. Let RA approach RS. Okay, well then, if I look here at d tau A over d tau B, RS over RA, that's going to be approximately 1. Okay, so therefore RS over RA is approximately 1. So 1 minus RS over RA is heading for 0. Okay, so that means that d tau A over d tau B, it's heading for 0. Okay, this ratio. And that means that the top line is much, much, much less than the bottom line. So d tau A is much, much less than d tau B. And in fact, if you really were to let the clock A go right all the way down to being exactly at RA equals RS, so right at the Schwarzschild radius, then d tau A would be 0. Okay, if you just put RS exactly equals RA there, you get d tau A equals 0. What does that mean? It means if I am an observer standing out here at point B, and then this clock A, if it's at the Schwarzschild radius, it will appear to be frozen. Okay, so the clock at the Schwarzschild radius appears to be frozen. So time dilation is actually, in the absolute extreme case, the time totally stops at the Schwarzschild radius. And that means that not just a clock, but any process at all on the Schwarzschild radius, to an external observer, it will just appear to be frozen completely. And that's a black hole. Okay, so because processes are frozen on the Schwarzschild radius, anything that's inside, so any matter or even any light that's inside the Schwarzschild radius, if it tries to escape, it can't. Okay, at least not as far as any external observer is concerned, because everything is frozen. Okay, everything on the Schwarzschild radius is frozen. Time literally comes to a standstill there. So that's why it's called a black hole. So if your mass distribution is entirely contained, if your mass distribution is entirely inside the Schwarzschild radius, it's called a black hole because nothing can escape, not even light. Okay, because everything is just frozen on the Schwarzschild radius. So, and in that case, there's another name for the Schwarzschild radius. So if you have a black hole, then it's called the event horizon, because anything that happens inside it can't be seen from outside. Okay, so that's what a black hole is. Okay, anything that falls in, it can't get out again. So in the next video, what we're going to look at is a little bit about motion of planets or other objects in the gravitational field of a black hole.